All right, welcome to the Explainer. Today, we're going to break down the 3 things that are, seriously, the absolute foundation of all electronics: voltage, current, and resistance. These are the invisible forces that make, well, pretty much everything in our modern world tick. I mean, think about it, right? We flick a switch, we tap a screen, and poof, something happens. But what's actually going on under the hood? What's that secret language that all circuits speak? Well, stick with me, because by the end of this, you're going to be fluent in it. All right, here's the game plan. We'll start with the basic playground for electricity, the circuit itself. Then we'll meet our 3 main characters: voltage, current, and resistance. After that, we'll see how they all link up with one beautiful formula. And then we'll wrap it up by looking at the real world and, how to stay safe. Okay, so first up, before we can really get the forces at play, we need to understand the playground they all operate in. And that, my friends, is the electric circuit. So any circuit, doesn't matter if it's in your car or your TV remote, it needs these 3 basic parts. You've got to have a source, like a battery, that provides the energy. You need a load, which is the thing that uses the energy, like a lamp that lights up. And you need a complete path, the wires, to connect everything in a loop. And if you break that path anywhere, say you flip a switch to off, the whole thing stops. It has to be a complete closed loop. So, what's the spark? What actually gets things moving in the first place? That's where voltage comes in. You can think of it as the go signal for electricity. Okay, to really get this, the best way is this classic water analogy. Imagine a big water tank way up high. Just by being up there, it creates pressure. All that water is just sitting there. It wants to go down, right? But it can't, not until you open a valve. That built-up pressure, that potential to do work, that is a perfect picture of voltage. It's the electrical push that's just waiting to be unleashed. As you can see here, it's also called Guerrillon. So to get a little more technical, voltage is the difference in potential energy between 2 points. It's really all about the work or energy per unit of charge. But here's the bottom line. No voltage, no push. Without that push, all those little charges, they just sit there. Nothing happens. It's the motive in electromotive force. All right, so we've got the push, that's voltage, but what is it actually pushing? That leads us straight to our next player, current. So let's jump back to our water tank. If voltage was the pressure building up, then current is the actual water flowing through the pipe once you open that valve. It's how much water is actually moving. In a circuit, this is the flow of charge, or as you see here, Occam. Okay, so we measure current in something called amperes, or amps for short. Now get this, 1 amp is 1 coulomb of charge moving past a point every second. And 1 coulomb? That's about 6.25 quintillion electrons. That's a staggering number. So when we're talking about current, we're talking about a massive river of charge on the move. Okay, so we've got a push, that's voltage, and we've got a flow, that's current. So what stops that flow from just being, infinite? What's holding it back? That's where our third and final piece of the puzzle comes in, resistance. Let's finish up our water analogy, because it works perfectly here too. So imagine that pipe the water's flowing through. What if we squeeze it, make it narrower? That's going to slow the water down, right? Well, that's resistance, which you can see here as D-wrench. That's exactly what it does in a circuit. It's like electrical friction. So resistance is just a property of a material that opposes that flow of current, and we measure it in ohms. And here's a key thing. The load in our circuit, remember the light bulb, that is a resistor. The whole reason it works is that the filament resists the current so much that it heats up and glows. So resistance isn't a bad thing at all. In fact, it's absolutely essential for making electricity do useful work for us. Okay, so we've met our 3 key players. We've got the push, voltage, the flow, current, and the friction, resistance. Now for the aha moment, how all 3 of these things are connected in one super elegant way. You'd think it would be a really complex relationship, right? But this physicist, George Ohm, figured out it's actually incredibly simple. And his discovery became like the most fundamental law in all of electronics. And there it is. V equals I times R. Voltage equals current times resistance. It's that simple. This little formula, this is the blueprint. This is the key to understanding, predicting, and designing pretty much any basic circuit. It tells you plain as day that if you keep the resistance the same and you crank up the voltage, the push, you're gonna get more current, more flow. It's a direct relationship. Okay, let's break this down with the table because this makes it super clear. Look at that first row. Resistance is constant. You increase the voltage, guess what? The current increases. Makes sense, right? More push, more flow. But now look at that third row. This is the cool part. The voltage stays the same, but you increase the resistance. You squeeze that pipe, and the current decreases. It's the other side of the coin. More friction means less flow. See how that works? This simple logic is what lets us control electricity. Okay, that's the theory. It's awesome. But let's bring it back to the real world. How do we actually measure this stuff? And maybe more importantly, how do we stay safe? So if you grab a tool called a multimeter, you can actually measure all three. For voltage, you just connect your meter in parallel, which means you just touch the probes on either side of what you're measuring. Now, for current, it's different. You actually have to break the circuit and put the meter right into the path in series, so all the current has to flow through the meter. And for resistance, this is super important. You have to make sure the power is totally off. Then you just measure across the component, just like with voltage. And that brings us to, honestly, the most important part of this whole thing, safety. Look, electricity is an amazing tool, but you have to respect it. Rule number 1, never ever assume a circuit is off. Always, always check with your meter first. Rule 2, water and electricity do not mix, ever. Keep your hands, your tools, your whole area dry. And finally, those little fuses or circuit breakers, they're not suggestions. They are there to save your equipment and maybe even save your life. Do not mess with them, don't bypass them. So there you have it, the push, voltage, the flow, current, and the friction, resistance. Now you speak the basic language of electronics. So look around you right now, your phone charger, a light switch, the toaster. You now get the fundamental code that makes all of them tick. The question is, what do you see differently now?